अच्छा, ये मैं जल्दी से करूँ कि जस्ट अ क्विक रिकैप के वो वी स्टडीड के why are transition metals colored. तो आई टोल्ड यू कि when you have stable ions transition metals their outermost shell, ठीक है, that's your the outermost shell is your d shell. ठीक है, it contains 5d orbitals. ठीक है, dxy dxz dyz dx square minus y square dz square, and two of them are on the axis. The electron density lies on the axis. Three of them, their electron density lies in the middle of the axis. Okay, they're all in different planes and they all lie between the axis. So all five orbitals are have the same energy level. They're identical. The orientation is only different. Okay, the Z one looks kind of different. So ये सब हमने किया था, and I told you that when a transition metal ion attracts all these ligands, so I told you कि the ion, the outermost shell is your the outermost, sorry, subshell is your D subshell, right? So the D has orbitals that are between the plane, between the axis and on the axis. So when it's an octahedral complex, so what happens is it's harder to keep electrons on the axis. It's a lot easier to keep electrons between the axis. So your D subshell splits. It no longer is identical. All the orbitals are not no longer identical. Some of them it's harder to keep electrons, so the electron has to be more energetic. Like on the axis, the green ones, much harder to keep electrons over there. The pink ones a lot easier to keep electrons over there. So the pink ones are the ones that are between the axis, and your green ones are the ones that are on the axis. So that creates an energy gap between the d subshell, and since it's incompletely filled, electrons can sort of switch between the d subshell orbitals. And they do that by absorbing energy that's coming from the visible light. So they might absorb a certain color energy. The delta E, the energy gap, is proportional to frequency. If the energy gap is bigger, you absorb a higher frequency. If the energy gap is smaller, you absorb a lower frequency. So the electrons are basically they can switch around between between the low energy d orbitals and the high energy d orbitals, and they might absorb a certain frequency from the visible spectrum. And so you see a complementary color. So if white light is coming and all the frequencies are coming in, the reflected light will have one frequency missing that it absorbs. So if it absorbs yellow, you're not going to see yellow. You will see all the other colors, but you will not see yellow. Okay. So that is how why transition metals were colored. So this is what we learned, that due to repulsion from lone pairs of ligands, the d subshell splits into two energy levels. Electrons from low energy d subshell orbitals gain energy and move to higher energy d orbital. And the energy gap delta E matches frequencies from the visible spectrum. And since E is proportional to frequency, hence a complementary color is seen. ठीक है, ये सारों को clear? Is this clear?
Yes, sir.
अच्छा,
Yes, sir.
so I just wanted to complete this, that the other thing they're going to ask you is I'm just going to quickly talk about a tetrahedral complex. So what happens in a tetrahedral complex is that the this splitting is going to be different. Okay, so the only difference in a tetrahedral complex is, I mean, there are all sorts of complexes, but we'll just talk about tetrahedral at the moment. So in tetrahedral complexes, the ligands are approaching, they're not approaching on the axis. They have a 109.5-degree angle. So so it's harder to keep electrons between the axis. So it's harder to keep electrons between the axis. You need dxy, dxz, dyz. So it's going to be harder to keep electrons over there. So the orbitals that are at the higher energy level are going to be these ones. Okay, so it's just going to be the opposite. I mean, it's going to be the same thing except that the orbitals that are having the higher energy level, they will, and the electron could be moving from the lower energy d orbital to the higher energy d orbitals. That's the only difference. Okay. So यहाँ पे it's all the ligands approach on the axis in an octahedral complex, while if it's a tetrahedral complex like the ones that we did before, यहाँ पे, for example, this one, then the ligands are not on the axis. They're somewhere between the axis. Okay. So which is why it's going to be harder. Like if you have a d subshell over here, it's going to be harder to keep electrons in between the axis. Okay. Is that clear?
Yes, sir.
So basically, that's the only difference. So so just keep okay. So just keep this in mind. And then there's another thing. They also ask you why do changing when you change a ligand. Okay, so they also ask you this that if you change one second. Achha, so they also ask you that if you change the ligand, why does the color change? Like if it's copper seal, why does changing ligand change its color? So because if you change a ligand, for example, over here, if you have a different ligand, for example, if I have ammonia over here, then what happens is that the repulsion that ammonia's lone pair is different than oxygen's lone pair in water, and that will create a different repulsion. So if you have a different ligand, the energy gap that is created is going to be different between the D subshell. So if I replace the water with OH ions or with NH3, the repulsion would be a lot different, which is why the energy gap is going to be a lot different. No two ligands are exactly the same. They're not going to cause the same amount of repulsion, which is why the energy gap that's going to be created is going to be different. And if the energy gap is going to be different, then energy is proportional to frequency. So the frequency from the visible light that they're going to absorb, that's going to be different as well. Okay, is that clear? That why changing ligands changes the color of the complex. Is that clear?
Yes, sir. Yes, sir.
Okay, so that's the second question they're going to ask you. So I'm just going to write the answer over here. Why?
सर जितना जायंट लैगेंड होगा उतना ही ज्यादा एनर्जी कैप है.
It would depend, because we don't know. Like, if I don't know if there's ammonia and there's water, right? So I think that water's lone pair has a higher charge density compared to ammonia's lone pair. So water's lone
ओके
pair
सर.
is going to create a much bigger energy gap. Okay. So
सर.
why changing ligand changes the color of complexes? Okay, that's the question. And the 3 mark answer to that is that different ligands have different ligand lone pairs have different charge density and cause a different amount of repulsion. So delta E that's created, the energy gap delta E created when the D subshell splits is different. And since the energy is proportional to frequency, hence a different frequency is absorbed. And so different frequency is absorbed and a different complementary color is seen. Okay, is this clear?
Sir, was like hence a different what? Like hence a different complexes observed or frequencies observed?
If you change the ligand, so the color of the complex would change, right? Because if I bring in another ligand, okay, एक second, just 1 second.
No, sir, I mean like the sentence your hands are different.
अच्छा,
What's
different
after that?
different ligand lone pairs a different charge density and cause a different amount of repulsion created when the D surface is different, since E is proportional, hence a different in different frequency is absorbed.
Okay, sir.
ठीक है यहाँ पे
सर अगर डिफरेंट लाइगेंड है लेकिन उसकी चार्ज डेंसिटी सेम है, मतलब किसी और की, तो
फिर सेम
दोनों के सेम कलर होंगे?
या approximately similar colors here.
ओके सर।
ठीक है. So it all depends. Okay. Plus it depends on the geometry as well. Na? क्योंकि if the geometry of the complex changes, then then the whole thing changes. The splitting pattern would also change, right? The way that we
यस।
discussed over here. Okay. I mean, if you have CuH2O6 and you become CuCl4 2 minus, so the geometry of the complex changes as well. And in the tetrahedral complex, the splitting is completely different. ठीक है. So is this clear?
यस सर।
So that was the I guess that's the last thing. The other stuff that's left is probably K stability. Okay, there's an equilibrium constant which we did not discuss when we were talking about equilibrium. And that has something to do with this. Okay, this thing is known as K stab, or the word is stability constant. So it's simply stability constant K stab is basically the equilibrium constant for a ligand exchange reaction. So it's basically the Kc. So it's the equilibrium constant for a ligand exchange reaction in aqueous solution. Okay, so it's the equilibrium constant of a ligand exchange reaction. The ligand could be any ligand, but it has to be an aqueous solution. So for example, if I have an aqueous solution, so copper in aqueous solution would be copper surrounded by 6 water molecules, right? Okay, so the starting point is that the ligand is going to be water. Okay, that's an aqueous solution. And if I add a ligand to it and the ligand exchange takes place, let's say I add concentrated HCl. So it will become what? It will become CuCl4, 4 Cl lines. It's going to form a tetrahedral complex. It will have a charge of 2 minus, and the 6 water molecules are going to get knocked out. Okay, and I'm going to balance it. Okay, now this is a ligand exchange reaction that's happening in an aqueous solution. Okay, so the starting point is that you're going to have an aqueous solution, you're going to put in a ligand, and ligand exchange would take place, right? And all ligand exchange reactions are reversible. Like if I put in more water, it's going to go backwards, right? The water is going to knock out the Cl and this thing would form back again. So it's the equilibrium constant. What is the equilibrium constant? It's K stab. So it's the concentration of the products divided by the concentration of the reactants. So it's basically what it's UCl4 2 minus concentration. Actually, remember one thing that square brackets have two different meanings. When you put square brackets represent complexes, but they also represent concentration as well. So, so when you use case tab and you want to denote concentration, you just use one bracket. You just use the concentration bracket. That's it. So then it's water concentration. That's going to be power 6 and divided by your CuH2O6 concentration. That's plus 2 and Cl minus 1 concentration. That's going to be power 4. Okay, so is this clear that it's just the equilibrium constant for a ligand exchange reaction? Is that clear?
Yes, sir.
Okay, now and also remember that water's concentration is taken as 1 in aqueous solution. You can remember when it's an aqueous solution, you don't write water because water is in large excess and its concentration does not change. So its concentration is taken as 1. It's not written in the expression. So we need to, so this is not, it's the same way that you don't write solids. You don't write water in the expression if it's an aqueous solution, which in this case it is, it's an aqueous solution. So this thing is going to be removed. You don't write this. Is this clear?
Sir, only for case tab के लिए.
हाँ, क्योंकि you're not going to write water in the expression.
ठीक है.
Because it's ligand exchange that's happening in an aqueous solution. It could be any ligand, but you don't write water in the expression. Its concentration is taken as a constant. Okay. Clear? Is this clear to everyone? Yeah.
You asked like in aqueous solution. So when is water like when we use water in the equation?
You're never going to use water because case tab is specifically for an aqueous solution.
Okay, I got it.
Okay. So water is not going to be written in the expression, and sometimes the same thing could be written this way as well. That the CuCl4 2 minus and this CuH2O6, they'll just write Cu2 plus aqueous. That's it. So sometimes you'll see that CuH2O6 just for convenience, they just write it as Cu2 plus aqueous. Okay, is this clear as well?
Yes, sir.
So all the ligand exchange reactions that we did, they all have a K-stab value. All of them have a K-stab value. So for example, any of the ligand exchange reactions that we did earlier, okay, we wrote down equations as well. So so for ex I mean this one we already did. So for example, not this one. This is not really ligand exchange. That it was a press plate that was dissolving to form a complex. Um, so we can look in the past paper and we'll find more equations. Okay. The one that we had, we already did. There was, but I'll just write one more. Okay, but is this clear that what a ligand exchange is? Sorry,
Yes, sir.
what a case tab is?
Yes, sir.
So I'm just going to write one more. Let's say I've got nickel with H2O6 and I add ammonia to it. And I add 4 ammonia to it. And a ligand exchange happens. So nickel now is surrounded by four NH3s. It's surrounded by four NH3s, and there are two water molecules that are left. And this overall charge is +2. And you've got four water molecules that are knocked out. Now, the K star for this reaction will be, the expression would be, it's going to be my product, which is nickel and NH3 4 and H2O2, and it's +2. You don't write water in the expression, okay? So water is taken as a constant, so you ignore water. Divided by nickel with 6 H2Os. ठीक है, बल्कि this is constant. Bring the +2 in. And NH3 4. NH3 power 4. And sometimes you'll also see the same expression, but they'll just ignore the water. They'll just write nickel aqueous. So you'll just assume that that's nickel with 6 H2Os. And even in the numerator, they'll just ignore the water. Okay, so is this clear? You clear? 100% clear, no? Right?
Yes, sir.
Yes, sir.
So now two things about K-stab. If K-stab has a large value, will there be a ligand exchange or will there not be a ligand exchange? Like if it's got a large value, will there be more products or more reactants?
More products.
There's going to be ligand exchange, right?
Yes.
So if it's got a large value, that means you're going to have more products. There's going to be more ligand exchange will happen very easily. And that also means that the product complex is more stable. And obviously vice versa, that if you have a small value, then it's going to be the opposite. Then that would mean that your reactant complex is more stable. And the ligand exchange is not going to happen. The product is not going to be formed. ठीक है? You clear? Is this clear? This part?
Yes,
Yes,
sir.
sir.
So then I guess we are. Let me just double check this one. So we did the isomers, we did all of this, deduce the. So we did case tab. I think in the syllabus they're actually very specific that write an expression. The case tab of a complex H2O should not be included. I mean, now they're being very specific. I mean, this is a new syllabus. So I guess use this then. I mean, the syllabus is telling you to write it this way. Okay, that's the new one, 2025, 2027. So use this only now. Okay, in the past papers, you'll see both. But I think the recent syllabus, you use this one. So make sure you use this one. We'll just stick to the syllabus. And yeah, we're done. We're done. We did electrochemistry previously. Redox, we did that in electrochemistry. And nothing new.
Sir, which chapter will you start next?
We just left with organic basically. Yeah, that's the so we're left with organic. So
have you done the first one, what's it called? Lattice energy?
yeah, we've done that. There would be lectures. I mean, the first few lectures would all be in the folder, right?
Oh, I wasn't there at that time.
See, I mean, the first we will do that again after this, but as well. But the first few lectures, like the first 5, 10 lectures, they're all on lattice energy.
So first 5, 10 lectures you did electrochemistry and lattice energy?
Yeah, I think so. Let me just double check this. 1 second. Yeah, I don't have it's in the drive folder, okay? I'll check.
Yeah, okay.
I mean, you can check if it's not there, I'll send them to you.
Yeah, I'll check.
So then you have 1 second. Where's the worksheet? I said remember the transition metal worksheet. That's kind of. I mean, whatever we studied, it's just that. There's no. I mean, there are not going to be any creative questions on that. Pretty much standard questions. Whatever we studied, the same thing would appear. So
So you would do the organic chem and then and then revise the other chapters and then we just do past papers?
yeah.
Okay.
Okay, this one. So this one is seeing this copper. It's given you. So remember, the questions will be very straightforward. Most of them are going to be very straightforward. So copper is with water. It's a complex, and he says separate portion of the blue solution react with aqueous NaOH and with concentrated HCl. So he's saying reaction with NaOH. What happens with NaOH when you add NaOH to it? So what happens is that you have to write the ionic equation as well. So Cu with 6 water molecules plus 2. When you add the OHN, precipitation happens. And the copper combines with the OH and forms this pale blue precipitate, and the 6 water molecules are knocked out. So a solid precipitate gets formed. This is aqueous, and that's a liquid. The type of reaction is known as, that one is known as precipitation. And the color of the complex is it's a pale blue precipitate. Do you remember we did all of that for cobalt and for you've done all of that. Okay, that's these complexes. It's copper with water. You add OH ions, the water molecules get knocked out and are replaced by OH ions. But with OH ions, it becomes neutral, so it no longer attracts water molecules even. So just becomes a copper hydroxide ionic solid, right? All the ligands they sort of break away because they're no longer attracted to something that's neutral. And we wrote down the equation as well for that, which was somewhere over here. That copper so this is the equation that they were talking about. I said next one, if you add HCl, what happens? What happens? What's produced?
So it will be CuCl4.
Okay, so +2, and it's going to form 4 Cl ions are going to come in and they're going to knock out the water molecules. It's going to become CuCl4, 2 minus, and the 6 water molecules are going to get knocked out. And this is ligand exchange. And the color of the complex, that's greenish yellow. And so now next one is actually a moles question. Um, I mean, should we do that or not? I mean, it's a moles question, and it's a very tough moles question actually. I mean, let's try and do that. He says 0.303 grams of a chloride of sulfur. Not a very tough one. It's 0.303 grams of a chloride of sulfur. So we don't know what that chloride is. So S, X, and CLY. I don't know what X and Y are. So he says it gets completely hydrolyzed in water, which means, and the chlorine atoms present in the chloride of sulfur are converted into chloride ions. So I have no idea with that it dissolves in water and forms Cl ions. So it's going to form YCl ions. They've given me the mass of this, 0.303 grams. Now the solution is diluted to 100 cm cube. So he adds water and makes a 100 cm cube solution out of it, and then only takes 25 cm cube sample. So he takes 25 cm cube of this, which is Cl ions. It's got Cl ions, and he titrates it with silver nitrate. So this is the reaction that's given. The silver ions will react, and they'll form a precipitate of AgCl. Now he's told me how much silver nitrate reacts. That's 22.4 cm cube, and the concentration given is 0.05 mole per dm cube. So that's the whole process that's happening. Took a chloride, an unknown chloride, converted it into Cl ions, diluted it into a 100 cm cube solution, then took 25 cm cube, reacted it with silver ions to form the precipitate. So how many moles of silver? What is he asking? He's asking for the empirical formula of this thing. He's asking for the empirical formula. So can you tell me how many? Now the only moles you can find out in this whole process is, because you don't know what the MR is, you can't find the moles. You can't find the moles. The only moles you can find is of silver ions. Can you tell me how many moles of silver ions do you have?
1.12 multiplied by 10 to the minus 3.
Multiplied by 10 power minus 3 moles, right? Concentration times volume. So Cl ions will also have exactly the same moles. 1.12 times 10 power minus. It's 1:1. Okay, is that clear? So if Cl ions, that's the amount that's present in the 25 cm cube sample. So what is the amount of moles in 100 cm cube?
We will just multiply by 4.
Okay, so in 25 you got this much. So in 100 you're going to get 4 times more. So what do you get if you multiply this by 4?
4.48 multiplied by 10 to the minus 3.
Okay, so you found this. Now the tricky part. How do you find the empirical formula of this? Well, what is the next step? You have to find the empirical formula of this. But what is the essential thing that's needed to find the empirical formula?
MR?
You don't need the MR. Empirical formula, you don't need the MR. Like if you try and remember the empirical formula questions, what do you need when you want to find the empirical formula? You need the percentage mass of the two things or the mass of the two things, okay? I mean that's the
Okay.
so can you figure out the mass of Cl? You have the moles of Cl, right?
We will use the MR
So you can find the mass of Cl, right?
of Cl, like 5.5.
Okay, so the mass of Cl will be the moles 4.48 times 10 power minus 3 multiplied by the MR, the AR of Cl, which is 35.5. So how much mass do you get?
0.159.
And all of that is coming from this thing, right? This is the thing that produced all that Cl. So get that 0.159.
Yes.
So what is the mass of sulfur in this then? It's going to be 0.303. Subtract 0.159 from it. So what is the mass of sulfur?
0.14396.
0.144 grams T. Now you are ready to find the empirical formula because you know the mass of the two things. What you're going to do is, क्या होता है steps for finding empirical formula? You divide by the AR first, right? So this is going to be divided by 32.1 and this gets divided by 35.5. इसका तो answer we already know. That's 4.48 times 10 power minus 3, right? What do you get for the other one?
4.4859 multiplied by 10 to the minus 3.
So again, that's approximately 4.48 times 10 power minus 3, right?
1:1.
1:1. Okay, so that's S1 and Cl. 1, that's the empirical formula. Okay, is that clear?
Yes, sir.
Yes, sir.
Okay, remember, a lot of times,
Yes, sir.
A levels most questions are like they can be kind of tricky. They can be very tricky actually. Uh, the people can get stuck in this question at any point. I mean, this was a tough. I mean, in hindsight, this was a tough question. I mean, it's a tough question to get the whole question right in one go. Okay, but is the question clear?
Yes, sir.
Okay, because A levels most questions will connect a lot of things together. Okay, but the empirical formula is connected with the whole dilution thing as well. So a lot of different moles questions question types will get connected in one question. So moving on, let's do another one. So that was just a moles question. The electronic configuration of copper 2 ions, that's 2p6, 29 electrons, right? So it's after that it's going to be 3s2, 3p6. Then for copper it's actually 3d10, 4s1. But since it's copper 2 plus we're talking about, so there's just going to be 3d9. Again, the same thing. State the color of the solutions. This is blue, and this is what? This is greenish yellow. Is that clear?
Yes, sir.
And this is the same question. It's a 2-mark question. Different ligands can have different colors. So why do they have different colors? Because different ligand lone pairs, but it's the same question. They're going to ask you typical questions. So different ligand lone pairs exert a different repulsion on D subshell. And a different energy gap gets created when D subshell splits. And since energy or delta E energy is proportional to frequency, a different frequency from the visible spectrum. Yeah, I guess it's just 2-mark questions. That would be sufficient. Okay, is this clear?
Yes, sir.
That's the next one. Why are the copper 1 and silver 1 salts colorless? I'm going to explain what copper, this thing, I mean, I did explain to you, uh, but we didn't write this down. But copper 1, right? Copper 1 is argon followed by it's 3d10 and 4s1. So plus 1 means that the 4s electron is lost, right? Why, what happens? Why is this salt not going to be colored? If the D subshell is completely full, why would it not be colored?
एक्सिस में नहीं
Sir, it
होगा.
will happen. Yeah.
Nahi. See, if the
Sir,
D,
it will happen.
see if the D
The
subshell is,
repulsion would be equal.
everything would happen the same way. But if the D subshell is completely full, the electron from the lower energy D orbitals will not be able to jump to the higher energy because there's no space available. Okay? The only way electrons are jumping around is because there's space available. There's empty areas available, right? So electrons can move from a higher energy to a lower energy and from a lower energy to a higher energy, right? But if it's completely full, the electrons will not be jumping around. Is that clear?
Yes, sir.
Yes, sir.
So well, यहाँ पे I'm just going to add this somewhere over here. Okay. Uh, that if you have a full d subshell, then electrons cannot jump around. Okay, cannot be promoted, or they can't absorb energy. Because there's no empty space available. Where would they go if they absorb energy? So they wouldn't be able to switch their d orbitals. So you need some empty spaces so electrons can jump from one to the other one. So it's a 2-mark question. So you're going to state that, you're going to state the same thing, that electrons, the d subshell would be completely full, and electron from a lower energy d subshell will not be able to absorb frequency and move to a higher energy d orbital. Okay, is this clear?
Yes, sir.
Yes, sir.
Okay. So, okay, let's continue. We'll continue on Monday. Okay, we'll probably do some more questions, and we might start with organic. Okay.
Okay,
Okay, sir.
sir.
Allah Hafiz.
So, okay. Take care.
Okay, sir. Is it मीटिंग में लीव